Thank you to Matthias, Sylvie, to all the organizers for this invitation. I changed a little bit the title of my talk, and I will focus on some stability and instability properties for a model which is quite famous in boundary layer theory, which is called the triple deck. And all the results that I will talk about are based on two joint works, one with Helge Dietert from my university, Université Paris-Cité, and one joint work with Samir Ayer from UC Davis and with Yasunori Maekawa from Kyoto University. Okay. Well, as usual in boundary layer theory, the motivation is the understanding of high Reynolds number flows near a boundary. So typically, what we will consider is a half plane. I will be in 2D for the whole talk. And in this half plane, we have the usual Navier-Stokes equation with the inverse Reynolds number that I denote by nu. Okay, and this guy will be very small. And the main feature is that at this boundary of at the boundary of the half plane, you have the usual no-slip condition. So of course, as we are in 2D, for smooth initial data with compatibility conditions, you have smooth global solutions, and you have bounds on your solutions, the bounds you want. Okay? But the problem is that these bounds are not uniform with respect to nu. Typically, you cannot have a uniform bound in a space like LP in time h1 of omega, or more generally, you cannot have an h1 bound in the vicinity of the boundary. And it's very easy, because if you had such a bound, then by compactness, you would have an accumulation point of u nu, which would satisfy Euler. That's the first thing. But also, due to the continuity of the trace on h1, you would recover the Dirichlet condition at the limit. Okay? And as you know, Euler flows, they satisfy the non-penetration condition. The normal component of the velocity field is 0, but the tangential component is not in general. Okay? So you cannot expect a uniform bound like this, a control of the gradient near the boundary. Okay? And of course, this is really related to the boundary. If we consider the implicit limit, nu goes to 0, in a domain without boundaries, the torus, the whole space, then you could differentiate the equation as many times as you want, and at least in small time, you would have uniform HS bounds, and you could go to the Euler solution. Okay? So there is really a concentration near the boundary, meaning that the gradient of the velocity field explodes as nu goes to 0 near the boundary in this region that Anne-Laure described in her lecture, the boundary layer. Okay? So the whole point is to describe this boundary layer. And okay, if you open a textbook on fluid mechanics, usually you have one chapter on boundary layer, and the first name that appears in this chapter is the name of Ludwig Prandtl, who made a big step forward by suggesting some asymptotic model for u nu. And this asymptotic model was based on an idea, I think, that was very new at that time, the matched asymptotic expansions, meaning that you have different asymptotics depending on the region of the flow. So what Prandtl suggests is that away from the boundary, where you expect no concentration, u nu should be close to the Euler flow. You could expect something regular in nu, and the limit would be the Euler flow. But as I explained, near the boundary, you should reflect this concentration. And Prandtl suggests the most natural scaling, which is the same one as for the heat equation, with concentration at scale square root of nu. So based on the parabolic part of the Navier-Stokes equation, and taking into account the divergence-free condition, it's very natural to suggest or to postulate that the horizontal velocity field will depend on t and x, usual time and tangential variable, but on a rescaled variable transversally to the boundary with this typical scale square root of nu. Okay? And for the vertical component, due to the divergence-free condition, you have to rescale by factor square root of nu. Okay? So this is, of course, a formal asymptotics, but that's the one suggested by Prandtl. And if you believe in it, then you can plug this into the Navier-Stokes equation. You can keep the leading order term, and you end up with this system, which is a kind of degenerate Navier-Stokes equation, which is called the Prandtl equation, where actually the forcing term is at infinity. The horizontal component of the velocity and the pressure should converge to quantities capital U, capital P that are related to the Euler flow. So there are three main features in this Prandtl system, this kind of degenerate Navier-Stokes. First, that's not the main one, but still it's important. In this reduced model, there is no horizontal diffusion for U, because the y derivatives hitting the y over square root of nu are more singular and they are retained in the limit, but the tangential derivatives go away from the original diffusion nu delta. So you lose the tangential diffusion. That's the first point. Then, okay, we've heard this term many times. In any anisotropic flow, you have this hydrostatic approximation, dyp equals 0, which means that p does not depend on y. But as I said, at infinity, it's given by the Euler pressure. Okay, so p is not anymore an unknown in the Prandtl system. It's a data. And as you can see, due to the hydrostatic approximation, there is no evolution equation on V. V is only recovered through the divergence-free condition. So at the end of the day, the Prandtl equation, you can think of it as a single evolution equation for one scalar equation, which is one scalar quantity, which is u, the horizontal component of the velocity. V can be seen as a functional of u, and p, as I said, is a data. So you've replaced formally the 2D Navier-Stokes by a single evolution scalar equation, which of course is very tempting. But unfortunately, life is not so easy, and it turns out that this appealing system, this Prandtl system, it has not so good stability properties. Okay? And to understand a bit where the stability problem comes from, it's a good idea to linearize this Prandtl system around some simple flow, which is a shear flow. Okay, so if you linearize the system that I wrote on the previous slide around this shear flow, okay, you end up with this linearized Prandtl system where you have a transport part, which is good. There is a diffusion part, which is at first sight good. And there is this thing, which is the contribution at the linear level of the stretching term, one could say, which involves V. But the problem is that in the Prandtl system, as I said, V is given through the divergence-free condition. And so this is first order in X. And the problem is that this is not a skew-symmetric operator. And moreover, and that's a big difference with the primitive equations we've seen yesterday, for instance, there is no tangential diffusion to sort of compensate for this guy. Okay? So you have this first order operator in X. And so at first sight, you could think that Prandtl equation is as bad as this kind of system, dtu equal absolute value of dx u. If you have something like that with some non-skew-symmetric term in X, well, here you can solve in Fourier, right? You take Fourier transform in X, And so you have dt of u hat k equal absolute value of k u at k. And then you find that u at k of t, that's exponential absolute value of kt u at k of 0. Right? And so you see that if you want some stability, so there is a huge growth because the growth rate is proportional to the frequency. So if you want some stability, at least for small time, you see that you need u at k of 0 to be less than, say, exponential minus delta absolute value of k for some delta positive, right? Because if you have that, as long as t is less than delta, you control the thing, okay? But then, okay, so you can first hope only for local well-posedness, and second, you have to impose this decay of the Fourier coefficient, right? And as you know, when the Fourier transform decays exponentially by Pele-Wiener theorem, it means that your data should be analytic. Okay, so at first sight, you can only expect for the Prandtl system some local well-posedness for X analytic data. But it turns out that the story is much more complicated than that. And okay, the well-posedness theory of the Prandtl system is a story in itself, but I won't detail too much. That's not the main topic of the talk. I just try here on this slide to summarize a few steps in this story. Okay. So actually, the first result was pretty old. It's back to Oleinik in the 60s, late 60s, where she proved local well-posedness of the Prandtl system for Sobolev data, so no analyticity, but with some monotonicity condition with respect to y of the horizontal velocity. So there is a structural condition of monotonicity in order to get local well-posedness. And this is because at the level of the proof, she uses a very smart transform called the Croco transform, which sort of turns Prandtl into a nonlinear diffusion equation where you have maximum principles, and from there you can construct solutions. Okay. And much more recently, this monotonicity case was revisited by Zuping Xin and Likun Cheng, by Alexandre and co-authors, by Masmoudi and Wang, who worked at the level of the Eulerian formulation of the equation without the Croco transform. Okay, but what happens then if you don't make a monotonicity assumption? So for the well-known result was local well-posedness for analytic data by Sammartino and Kaflish, 1998. And as I said, this corresponds to what could be expected if you look roughly at the equation. But actually, later on, and there has been a lot of activity around this in the last, I would say, 10 years, it has been proved that the situation is more complicated than that. So actually, you can show that for generic data, you don't have growth like this. Okay? So actually, the maximal growth for Prandtl is not this that you could have expected at first sight, but it's more like exponential absolute value of k1/2 t. Okay? Which means that you have to, you may sort of widen the space of your analytic data for which you can have local well-posedness. You can impose, it's still strong, much strong, I mean stronger decay, much stronger than the Sobolev decay of the Fourier transform. But it decays a little slower than analytic data. And this kind of decay of the Fourier transform corresponds to what is called Gérard-Varet 2 functions in the literature. So that's what I try to write here. If you have a function of x, it's in Gérard-Varet class S if its Fourier transform decays like exponential minus k to the 1 over s. Okay, so what we proved is that Prandtl is well posed locally in time in this space. So we proved first that it was ill posed for data with higher regularity. So we identified some instability mechanism of this kind. And then we did the other part. We proved that this instability is the worst possible in the sense that, and it's a result that I obtained with Helge Dieter 2 years ago, you have local well-posedness in this Gérard-Varet space. Okay? Yeah. Yeah. So the first, if you add monotonicity. What do you mean? It's local in time? I just wonder how. You have decay in y at infinity, but it remains positive. But it goes to 0. Yeah, that's right. But okay, you can control in weighted spaces. That's weighted Sobolev space. Okay. Okay. So that's well the well-posedness theory for Prandtl. Actually, there are many other works. There are people studying finite time blow-up for non-monotonic data. There are, on the positive side, almost global existence results for small data, small analytic, for instance. There is a recent paper of Paiku and Tang. Okay, and I will stop here for that. Regarding the mathematical properties of the Prandtl system. But actually, I mean, not only mathematically, but even from the point of view of physics and from the point of view of the engineering community, it's known that the Prandtl equation fails to capture some well-known boundary layer phenomena. And a famous example is the phenomenon of boundary layer separation that you can see on this picture. So, okay, let's say the tennis ball is fixed. You have air coming from the left. And, okay, upstream, you see that the streamlines get close, concentrate near the boundary. So that's a typical boundary layer behavior. And so you can expect in this region the Prandtl expansion to be true. But it turned out that if you have an adverse pressure gradient, so if the dxp, I had a dxp in my Prandtl equation, so if it has a sign corresponding to slowing down the velocity, then, well, you will have at some point an inflection point that appears in your velocity profile. And from there, you have some instability. And you can see in the picture this separation of the streamline. So the boundary layer, it detaches from the boundary. Okay? And it's clear. So here, well, actually, it's not so clear here, but you have vortices. And in this region, it's clear that the Prandtl ansatz is totally wrong. Okay, so that's one failure of the Prandtl boundary layer theory. But even without inflection points, even before the separation, you can have other problems due to a well-known hydrodynamic instability called the Tolmien-Schlichting instability. And the reason is the following. If you have concave Prandtl flows, so no inflection point, so no separation, of course, associated with this Prandtl solution, you can construct, in the way Prandtl did, some solution of Navier-Stokes, or some approximate solution. But think of it as a solution of Navier-Stokes. You rescale this Prandtl guy by the scaling I showed before. Okay? So in this way, you have a solution of Navier-Stokes of boundary layer type. And the problem is that this is a highly linearly unstable solution. If you look at the linearization of Navier-Stokes around this, well, the analysis is a bit involved. It goes back to works of Tolmien and Schlichting, first half of the 20th century. And you can show that the linearization around this solution has perturbations that grow very fast because you see here the growth rate is nu minus 1/4. So when nu is super small, that's a super large growth rate. Okay, so that's very unstable. And also you can see that the perturbation has some small scale in x. Typical variable for this unstable mode is x over nu to the 1/8. So here and in the separation problem as well, the main difficulty is that due to these instability phenomena, small scales appear in the tangential direction. Okay? And the problem of the Prandtl expansion is that you have a singularity in the transverse direction, y over square root of nu, but it's assumed to be regular in t and x, which is not true in these settings. Is that okay? I mean, don't hesitate to ask questions. Okay, so that brings me to the main focus of my talk, which is what is supposed to be an improvement of the Prandtl system, which is called the triple deck model. So what is the idea behind the triple deck model? So it's very well explained. I should have said that. I should have put it on the slides. There are lecture notes by Pierre-Yves Lagré, which are very nice on this. So the idea of the triple deck model is to restore small tangential and small time scales in the vicinity of some time t star and x star. So typically you can think of t star and x star as the time and location of separation, or often you can have a localized, roughness at your boundary. So there is a small scale due to the roughness of the boundary. And so you want to adapt this appearance of small scales in the tangential direction. That's the idea. So what you do from an asymptotic point of view is that you will add to the usual Prandtl ansatz, you will add some correction. This is called the main deck asymptotics. We will see why. And okay, this correction should be small. So you have a free parameter for the time being epsilon. You have, and you see that you have a small time scale eta and a small tangential scale delta that are still at this level unknown. Okay, so, but if you anticipate certain relations between these parameters, you can show, plugging this expansion in the Navier-Stokes equation, that this perturbation, u tilde v tilde, will satisfy a very simple equation. So you keeping only the leading order terms, you simplify a lot. And okay, I don't want to be too precise on the derivation because it's very lengthy. But you can show that this perturbation that you added can be expressed in terms of what I denoted here, capital U. So capital U is the original Prandtl flow frozen at this time t star and location x star. And it depends on an unknown function of t and x, which is called for the time being capital A. Okay, so you replace the unknowns u tilde v tilde by this capital A. You reduce the complexity, but it's still not over. And the problem also is that you see from this representation that this guy won't vanish at the boundary. So it does not satisfy the no-slip condition. So you have to add a sublayer, okay, to this main Prandtl layer, which is called the lower deck. So you have the main deck, the Prandtl layer, you have a sublayer that is called the lower deck, and you have what is called the upper deck, which is the Euler flow, or something which should be isotropic in the tangential and transverse variables. Okay? So as you can guess, plugging all this machinery into the equations, deriving the values of the different parameters is involved, but you can do it. It's explained here. You can typically, okay, identify the time scale delta and eta, which were unknown at the origin. And actually, you find the same time scales and tangential scale as in the Tolmien-Schlichting instability. So there is a rigidity in the kind of scales that appears in the system. And OK, let me drop this. At the end of the day, what you get is in the lower deck, I mean, the equation governing the lower deck, it can be summarized into this. So what is this? You have still an equation of Prandtl type, I would say. This is a dxp. So this is an equation of Prandtl type. But there is a strong change in in two respects. So first, there is a new condition at infinity. So you have u minus z, which should converge to a constant to this a of t and x. And the pressure is given by this non-local operator absolute value of dxa. Okay, so it's a bit strange at first sight, this system, but this is what is given by the analysis, okay, by the asymptotic analysis. So this triple deck system is well known now in boundary layer theory. It was derived in parallel by Stewardson, Neeland, Messiter, 1969, 1970. So now, mathematical question, is this system more stable than Prandtl? Because it was made to be more stable. It's not obvious at first sight because as you have a Prandtl type equation, you will have the same possible loss of one derivative, okay, that I was mentioning before. And moreover, on top of that, you have this strange relation where the pressure is given by the absolute value of dx applied to this a, and a is the limit of u minus z at infinity. So there is this very strange relation on the pressure. So, and moreover, as you can see, due to this, there are two derivatives in x here. Okay, so it could be even worse. I mean, it could grow like exponential k squared t. It could be a backward heat. Yeah, so it's like a Prandtl equation, but it's not in the original variables. Yeah, very true. It's really in the sublayer, the one that I call the lower deck. But as you have rigidities through your rescaling, well, as soon as you look at an anisotropic flow, something like a skeleton of the Prandtl equation appears. Okay, so concerning stability and well-posedness, I think the first rigorous work was performed by, was due to Ayer and Vicol in 2020, where they proved an analog of the Sammartino-Cavendish result for Prandtl. They proved local well-posedness for data that are analytic in X. And there is a technical condition, they need a lot of decay in Z. It's not so nice, but. So even to prove local well-posedness for analytic data is not obvious because, as I said, there is this guy, gx absolute value of dxa, which shows up. A is the value of u minus z at infinity, so it's a bit intricate. But actually, taking the limit at infinity of the Prandtl equation, you can recover an equation on capital A, which is called in the literature a Benjamin-Ono equation, which has dispersive properties. And of course, there is a coupling with the velocity in the layer. Okay, so but there is this Benjamin-Ono part, which is not so bad. Okay, and using this equation, they will have a good estimate on capital A in terms of u. But then, of course, to couple with u and to close the system, you need to transfer this good estimate, which is an estimate on the value of u at infinity, into the bulk. So there is a lot of work to be done, but they managed to do it. Okay. Okay. So question: as for the Prandtl system, can we expect better? Well, at first sight, we could expect better because first, the fluid mechanics community tells us that it's better behaved, at least for steady flows. I'm cheating a bit, actually. There is a lot of work on the steady triple deck model, but okay, you could hope for more. And also a good sign is that when you look at the triple deck model linearized around this linear flow, Z0, which is natural because you see in the triple deck model you have this Z here encoded in the model. So if you linearize around this linear shear flow, you can do computations by hand or almost by hand and prove that it's stable in the Sobolev setting. So this simple linearization is stable. Okay. Okay, but unfortunately, this simple example is misleading. And what we found with Helge is that when you linearize around something a little different, Z plus some US of Z, okay, if you linearize around some more general shear flow, things are not so nice. So this is the linearized triple deck. Okay. I write down the equation, but I won't need it. And what I'm claiming is that the linearized triple deck is actually even worse than the linearized Prandtl, in the sense of this theorem, which says roughly that there are, and actually there is a large class of monotonic shear flows for which the linearized triple deck model has solutions that grow like exponential k sigma naught t. Okay, so what I'm saying is that for a large class of shear flows, the linearization of the triple deck model around these shear flows has growing modes like, again, something that would be with a growth rate proportional to the tangential frequency. Okay? So actually, I'm stating a theorem like this to make it simple, but there is a more precise statement in our work with Helge. We have a criterion for instability. You give me a shear flow, and I can check if it's stable or not. And second remark is that this kind of growth is only, I mean, if you look for local well-posedness, it forces you to consider initial data that are analytic in X. So generically, the result by higher NV-col is optimal. That's what we show. Okay. So it's even worse than Prandtl. So how do we prove that these linearizations have growing modes like this? So I will try to give you a hint at the proof. Okay, so to prove this, we follow closely a strategy that we had already used in a joint work with Anne-Laure and Frédéric Marbach a few years ago on another model called the interactive boundary layer model. So what we do is the following. Okay, first we rewrite the system in terms of a stream function. Okay, so there is a stream function phi. We take the Fourier transform in X. We look for growing modes. So at the end of the day, when we inject growing modes in the equation or Fourier modes in the equation, we have an ODE system in the Z variable, right, in the transverse variable. And this is a third order equation. You have to do the calculation to see this. And you have in front this coefficient, in front of that's a diffusion term actually. In front you have this 1 over k. Okay, so if you look at stability properties, at well-posedness properties, that will be stability at high frequencies. So k will be very small, very large, sorry. So 1 over k will be very small. And okay, so this is the third order ODE in Z. And you have the boundary conditions, which correspond to the Dirichlet condition and the condition at infinity that I was mentioning. And okay, you can see that there is a compatibility condition hidden in this equation, and you have 4 boundary conditions for a third order equation. So you need, well, this is an eigenvalue problem. Okay. So we want to show that this eigenvalue problem has solutions with, well, the eigenvalue mu k that has a positive imaginary part. Then it will correspond to a growth, an instability, because I rescaled by k here. Okay, so to understand, I mean, we cannot understand this problem directly. It's too complicated. So we first look at the simplified problem where I drop the diffusion, which seems okay when k is very large. Okay, so I get rid of the diffusion. And of course, the system simplifies a lot. But of course, as you get rid of the diffusion, you have to reduce the number of boundary conditions accordingly. Okay, so, and there is a discussion. I mean, it's hard to identify the conditions that you need to keep. But okay, you keep these ones. So the stream function should vanish. And you impose u, that's phi prime, to go to 0 at infinity. So of course, as this is the first order ODE now, you can solve by hand. And you end up with this formula for the solution. And then injecting the boundary conditions, you see that the dispersion relation, or the eigenvalue relation, is given by this equation, where phi infinity is this function. Okay. So you had a shear flow Vs of z, which is z plus us, with this guy going to a constant. And now the eigenvalue relation is this with a function involving an integral of Vs. Okay. So we want to prove that this solution, equation has solutions in the half-plane imaginary part of mu positive. Okay. So how do we do that? We use complex analysis, and we use actually an idea that is well known in plasma community. When you look at the stability of equilibria of the Vlasov equation, there is a very famous work of Oliver Penrose in this context, where he adopts the same strategy. So we copy the strategy. So the idea is that this equation will have a solution in the half-plane imaginary part of mu positive if and only if a certain winding number of a curve is non-zero. So what is this winding number? So what you do is you consider a contour like this, with here a small parameter epsilon, so you are epsilon close to the real axis, and a large radius. And okay, this is really, this is standard complex analysis. So you look at the image of this contour by the function you are interested in, phi infinity, and you look if it winds around 0 or not. Okay? And actually, there will be a root in the unstable half-plane if and only if, for some epsilon small enough and r large enough, this curve, winds around 0. Okay? This is a standard complex analysis. So that's the criterion we use. And okay, and from there, okay, you start to study this curve I was mentioning. You can show that for r large enough, the image of this curve will be close to -1. This is what is expressed in this lemma. Okay, the image of this half circle will be close to -1, so it will not wind around 0. Okay, there is another lemma where you can exclude also that this part contributes to the winding. And then you focus on this part. And when epsilon, as epsilon can be taken very small, you have some kind of asymptotic process. You use formulas, which are called Clémenche formula. Well, in the end, you have some more explicit criterion. So you have to look at now the image. This complex function, you have to look at the image of the positive real axis, and you have to count the number of crossings of the positive real axis that it does. Okay. Well, it's everything is computable, and through this you can really exhibit analytically a class of shear flows for which this curve will wind around 0, and this means that you will have the large growth I was mentioning. Okay? And but more generally, this winding number criterion is very convenient analytically, numerically, sorry. So you have analytical examples, but you have numerical examples as well. So for instance, you can take this shear flow. There were supposed to be axes here. Okay. Anyway, you have to believe me that 0 should be here. Okay, so you can really compute. I give you this VS. You can compute the image of this contour, and you see numerically that for epsilon small enough, it will circle around 0. So I can tell you that this guy, the linearization of the triple deck model around this guy is super unstable. Okay. But of course, all I told you about was about the inviscid problem. I dropped the diffusion, taking k equal infinity in some sense. So, of course, at some point, we have to go back to the finite k case. So reintroduce the diffusion and show that the instability persists. And to do that, that's a kind of stability property of the instability in some sense. But what you need is to have some stability estimate for this kind of equation. And that's where actually we use the work we had done on Prandtl with Helge. We managed to use the stability estimates that we had derived for the Prandtl equation. We managed to use them on this problem, okay, which is a kind of sub-problem in the viscous, in the triple deck linearized model at k finite. Okay, so thanks to a stability estimate for this model, which is close to the stability estimate we had on Prandtl, we can prove that the instability that we identify at infinite k persists at finite k. Okay, in the sense that we managed to show that this dispersion relation for the finite k problem remains close to this dispersion relation that we had seen for the infinite k problem. And then you conclude by Rouchet's theorem. So if you remember your lectures in complex analysis, you know that if two functions are close enough, they have the same number on a circle. They have the same number of roots inside the circle. Okay, that's it. Okay. So that's it for this result showing strong growth. And but that's not the end of the story. I'm left with 15 minutes. So I would like to emphasize the role of convexity in this kind of problems. Because maybe, you had noticed that this strong instability that we identify in this triple deck model is really coming from the k equal infinity case where you drop the diffusion. So that's an inviscid instability mechanism. Okay? And as you know, inviscid instabilities in the Euler equation, for instance, they are related most of the time to inflection points. Okay, maybe you heard about the Rayleigh instability theorem. So you need inflection points to have inviscid instability. So you may expect, if your shear flow has some convexity or concavity, that things get better. Okay? And well, you can ask this question in the context of the triple deck model, but you can ask it in other contexts for other anisotropic models. The convexity plays a role in the stability property of the flow. And typically, this kind of problem appears in what I call the hydrostatic Navier-Stokes equation. So I don't know if it's really approved label, but what I mean is that, okay, if you look at a scene domain of size epsilon, and if you look at the Navier-Stokes equation, but not as in the last talk of yesterday, with an isotropic viscosity of size epsilon square, then you end up with a system which is a kind of Prandtl-like, but with other boundary conditions and other than the triple deck. And convexity will play a role in the stability property of this system. And this is what, I mean, we had a paper with Nader, Masmoudi, and Vlad Vikol around this. Okay, and the answer to the question, do we have more stability under concavity, is yes. And okay, we show that this exponential growth lowers a little bit. The growth rate actually falls down to k2/3 instead of k. So that's still violent. Okay, here I'm not claiming that it's stability. Okay, I'm just discussing the kind of instabilities we are facing. And what I'm saying is that the instability we are facing under concavity condition on the shear flow are less violent. Okay, and a rigorous statement would be this one, obtained with Samir and Yasunori. So if you assume some concavity of the shear flow, I prefer concavity because you go to a non-zero positive constant usually. So, okay, it's concave. So if you have concavity on your shear flow plus some natural decay conditions, and if you start from an initial data which has Geophysical 3/2 regularity in X and Sobolev regularity in Z, then on small times you can control this Geophysical norm. Okay, so there is a bit of a decrease of it deteriorates through time, but it's still Geophysical stability. Okay, so you go from the analytic world to the Geophysical world, and this tells you that the growth rate in this case cannot be worse than this. Okay, this is a way to express this. Okay. Stability, local stability in Geophysical 3/2 is a way to express this about the growth rate. Okay, so in the last minutes, I will try to tell you how we prove this kind of stability estimate. So what we do is that we take the Laplace transform in time of the equation, we take the Fourier transform in X of the equation, and we reformulate things. And you can show that the linearized triple deck model can be rewritten like this. So you have what corresponds to the Benjamin-Ono equation I was mentioning before. So we use this special structure very much. Coupled with an equation for omega. So omega is like the vorticity. But in the boundary layer context, the vorticity degenerates. So what I call omega here is just dy of the dyu, where u is the horizontal component of the velocity. Okay? That's the analog of the vorticity in this boundary layer case. So you have this coupled system, and you have this condition which expresses that the perturbation u should be converging to capital A at infinity. So it's a condition on u which is hidden here, but it gives a non-local condition on omega. And you remember the lecture of Edris Titi yesterday. He was mentioning that this kind of non-local condition in domains with boundaries is very annoying. Okay? And so I will try to explain to you how we handle it. Because we need to go to the vorticity level for some other reason, but then we have to deal with this guy. Okay? And okay, once we have come to this resolvent equation, the key point is to show that we can invert for the real part of lambda, which is more than k 2/3. Okay? If I'm able to invert for this range of lambda, it will tell me that the maximal growth rate is like this. Okay. Okay. So the general idea to prove this resolvent estimate is to proceed in two steps. First, we look at A like given, and we focus on the vorticity equation with this non-local condition. And we show that under this spectral condition, we can solve. For any A, we have a solution omega of A. And then once we have the solution of this subsystem, we plug it into the Benjamin-Ono equation for A. And the second step consists in proving that this equation is okay, again under this spectral condition. Okay? Let me mention that this condition and this growth rate seems to be optimal, actually. You cannot lower it. At least in the context of this hydrostatic system, it's clear. Okay, so these are the two steps, and actually each of them is difficult, is involved, at least for me. So I will just take a couple of minutes to mention how we deal with the first step. Okay? So as I said, the problem, one of the main problems is this non-local condition. So the way we prove well-posedness or invertibility of the resolvent is the following. So it takes inspiration from previous work, and especially a work of Nader, Maekawa, and myself. We solve by iteration. So it's like a splitting method in numerical analysis. We don't know how to obtain good estimates directly for this guy. We don't know. It's like a good estimate for the Or-Sommerfeld equation. Directly, we don't know how to do it. So what we do is, first, we deal with all the terms in the equation, including this bad stretching term, but with some artificial boundary condition. So I replace my non-local condition by an artificial one. And of course, then I need to recover this good boundary condition. But at this stage, I can only do it cheating on the equation. So there is an iteration, and at each step of the iteration, I have two sub-steps. One where I cheat on the boundary condition, and the other one where I restore the boundary condition, but I cheat on the equation. So of course, I have a new error now if I cheat on the equation. But then I have another iteration, and so on and so on and so forth. And I have to prove that this iteration converges exactly. So it's not like in the talk by Rupert, where you need, asymptotic expansion up to a finite order is enough. So I cannot cut at finite order because I have no stability estimate on this system. Okay. And so a last word. How do I control this system with artificial boundary condition? Well, it uses ideas used by Brenier and Grenier in the context of hydrostatic Euler equations. So this is exactly where convexity plays a role. The idea is really, once you see it, it's really simple. You instead of taking an L2 estimate for this system, you multiply not by omega, but by 1 over this guy, u prime prime s times omega. And if you do that, this guy vanishes. Okay, so the difficulty with the stretching term goes away. So that's the basic idea used by Brenier and then by Grenier. Okay, here we have to be better than that because to do more than that because if you take this guy at infinity, you have problems. It could put too much the decay condition on your solutions, but so we have to adapt it. But we managed to adapt it. But this is where also we need the Neumann condition because you see we do an energy estimate. So because of the diffusion, if we don't have a nice boundary condition, we will have a boundary term, and this will be very bad. So that's why we cheat on the condition. Okay, and then we have to handle the other guy. And here the trick is to prove that this guy has some boundary layer behavior where we gain powers of lambda, but it's becoming too messy. And I will stop here. Thank you very much.